Okay, let them through, and I'll the YouTube link. I'll put it up in a second.
Okay.
Let's see here. Okay. Morning, everyone. This is funny. Okay, I'm trying a test poll. Syed, do you see the poll?
Yes.
Can you see the results of the poll?
Yes.
Howard Xiao, could you unmute yourself?
Yes.
Do you see the poll?
I already did it.
Okay, what do you see? Do you see the results of the poll?
No.
And once you did it disappear?
Yeah.
Okay. All right, thanks.
Okay.
I wonder also, when people join, it must be that the poll just shows up as soon as they join. Okay, let me end the poll. This was a test poll. Okay, so the finite field FP has P elements in it. Okay, people? It does not have P minus 1 elements, and it does not have P plus 1. It has P. Okay, next time you should try to count them or something. Because I've got 9 plus 6, which is 15% of respondents. 15% don't know that FP has P elements in it. I mean, come on.
Are we being marked for this?
Well, no, you're not, but you're lucky that you're not.
Dang.
15%.
I got it right.
Can we be marked for this?
Yeah, we'll see. Okay. I need to test to see what kind of response it gives me, whether it gives me a CSV or some other type of file that I can actually work with. Okay. Okay, we'll start in a moment. Okay, so let me just, yeah, okay, very good. Okay, so the on Tuesday we went through the proof of a very important lemma, which is basically the idea that if you give me a list of vectors, that list, there's two possibilities, right? It could be linearly independent or it could be linearly dependent, okay? Linearly dependent means that there's a redundancy somewhere in the system. Okay, so when we say that, so just a brief review. So when we say that V1, Vn is linearly dependent, okay, this means that there's a redundancy. There exists a redundancy. So what does it mean, a redundancy? It just means that there's linear combinations of these vectors. So an example of a redundancy would be something like this, that the two vectors are just scalar multiples of each other, right? If this was V1 and this was V2, then you would see that, for example, A1 V1 plus A2 V2 is equal to 0, where some of the AIs are not 0. In this case, I would just have like V2 is equal to 2 times V1, or in other words, 2 times V1 minus V2 is equal to 0, like 2 times V1 minus V2 is equal to 0. This would be an example of a redundancy, that it's telling you that the vectors are somehow not all necessary in order to describe the span. There's a redundancy from the point of view of span. Okay, so that you don't need all the vectors in order to span the space that they span. Okay, that's what I mean by redundancy. So does that mean that all of the vectors need to occur in this equation? No. It could be that the redundancy only involves V1 and V2, and we don't even need V3 up to Vn in order to see that redundancy. Okay, so the condition, another example which I gave before was if I have 3 vectors in the plane which are all pointing in different directions, right? There's a redundancy among the 3 vectors, so there is a linear combination with coefficients which are not all 0, which they satisfy. Okay, so this condition of linearly dependent, okay, means that there is some non-trivial linear combination which equals 0. So in other words, we can find A1 up to AN, not all 0, okay, such that A1 V1 plus A2 V2 all the way up to AN Vn is equal to 0. Okay, so this is the meaning of linearly dependent. And if it's not linearly dependent, then it's called linearly independent. Linearly independent means that everyone is essential to bring that span. Everyone is essential. If you remove one of the vectors from that, you will not get the same span. Okay, now okay. Now let me just so I just want to get through an important piece of theory today before we do some more practical things. Okay, and the first is that we finally have we can finally approach the idea of dimension. Okay, and so let's do that. So the first important definition is that is that of a basis. So let me put it like this. So let V be a finite dimensional vector space. Okay, so we know what that means. That means that it has a finite spanning list. meaning that there is a finite list of vectors in it that span the whole space. Okay, so let's say that we have a finite dimensional vector space. Okay, so the idea of a basis is that, you know, if you give me a spanning list, there's things that I can do to it. I can always add an extra set of vectors to that list. I can always increase the size of the list by adding randomly some vectors, and that will still span the whole space. But I could also use the lemma to try to find vectors that are redundant. So if there are any redundancies, I can try to shorten the list. Okay, and at some point, you know, at some point the lemma will fail because the list of vectors is linearly independent, that there are no redundancies. And at that point, when we have no redundancies, that we've gotten to the minimal length of list that can span the space. Okay, and at that point, that's what we call it a basis. So a basis V1 VM. So a basis for V is a list of vectors which is, number one, spans V. So it's a spanning set. And number two is linearly independent. Okay, so right away, I'm going to give an example. So if we look at f to the n, okay, this is, you know, if you're working over a field f, then f to the n is your favorite, most standard vector space of dimension n. We haven't defined the dimension quite yet, but Fn we've seen is a vector space over the field f. And then this has an obvious or natural basis as follows. Okay, E1 will be just the vector which consists of a single one in the first entry. And then we go all the way to En 0, 0, 1. Okay, so, and the, you know, so for example, let's say that we wanted to prove that this is a basis. Well, first of all, we need to show that it spans the entire vector space, right? And so to show that, we just say that, you know, if I have a, so any vector in V can be written as A1, AN, where the AIs are in the field, right? That's what a vector looks like inside this vector space. And then we can immediately just, it's a very easy task to write this vector in terms of a linear combination of the basis elements. So we can say that it is A1 scalar multiplied on E1 plus A2 scalar multiplied on E2 all the way up to AN scalar multiplied on En. So this vector is this particular combination of the basis elements. So this shows that it's spanned. By this list. Okay, and to show that this set that this list of vectors E1 up to En is linearly independent, is linearly independent, what you need to do is show that there are no non-trivial linear combinations equaling 0. So in other words, if I have some redundancy, A1, so if A1 E1 plus AN EN, well, these are not, I don't want to confuse it with the previous scalars. Let me call them lambda 1 up to lambda n. If we have a non-trivial linear combination, if we have any linear combination equaling 0, then I can just compute this. If I compute this, what is this actually equal to? It's actually equal to the n-tuple of numbers lambda 1 up to lambda n. And if this is equal to 0, what is 0? 0 in the vector space f to the n is just 0, 0, 0 up to 0. So if this is equal to 0, this means that the lambda I are all 0 for all I. And so this means that we have that the linear combination is trivial. So this means that the only linear combination that can be 0 is the trivial one. So the linear combination is trivial, no redundancy. Okay, or in other words, there is no there is no linear dependence, and so these are linearly independent. Okay, so so this is your standard basis for the standard vector space f to the n. Okay, and it will often be the case that we're going to be presented with vector spaces that are not exactly this one. And you might be asked to find a basis. And this is not always the most obvious thing to do. For example, and we're going to do this next week. For example, suppose that I started with a really simple vector space. Suppose I started with R3. Okay. And suppose that we define a vector subspace, a linear subspace, consisting of, so the linear subspace is the following. It's the set of x, y, z such that x plus y plus z is equal to 0. So this, if I have a vector x, y, z, which satisfies this equation, and if I multiply it by a scalar, lambda x, lambda y, lambda z, it will still satisfy the same equation. And if I take one solution of this equation, let's say x, y, z, and if I find another solution, a, b, c, and if I add those two vectors together, x, y, z plus a, b, c, then the sum will also satisfy this equation. So the solutions to this equation form a linear subspace of R3. And it kind of looks like, it's kind of hard to draw in this projection, but it's a plane which is passing through the origin. Okay, and I'm drawing the normal vector to the plane. Okay, and so this is a subspace of R3, and it is therefore a vector space over the real numbers. Okay, and we may ask the question, find a basis for U. Can you find a basis for U, right? The reason why the answer is, the reason why it's not so clear or not so obvious how to proceed is that these basis vectors are very easy to find for f to the n. But when you have a subspace which is somehow inclined in in an interesting way and doesn't agree with the coordinate axes, doesn't agree with one of the coordinate planes, then it's not so obvious to find the vectors inside which form a basis. Okay, but we're going to have methods for doing that. Okay, I'm going to take just a quick question from Omar before I continue. Please go ahead.
Yeah, I just wanted to make sure in example 2 where E1 to En is linearly independent.
These are
we
just,
say-
sorry, just to clarify, I'm not giving two examples here. I'm checking the two properties for it being a basis.
Well, we know lambda 1 to n is equal to 0, 0, 0 because of the fact that E1, En is E1 to En is all equal to 1, right?
This is what E1 up to En is. Okay.
Yeah.
So if I take lambda 1 and if I multiply it by this, I'm just going to get a lambda 1 in the first entry.
Yeah.
Right. So if I take the sum, what I'm doing here is I'm computing this, right? So if I take lambda 1 times 1 plus lambda 2, 0, 1, 0, plus lambda 3, 0, 0, 1, then I get lambda 1, lambda 2, lambda 3. And if this is equal to 0, then it must be that lambda 1, lambda 2, and lambda 3 are all 0.
Thank you.
You're welcome. Okay, so the important thing after this definition is to prove the theorem that every finite dimensional vector space has a basis that exists, that there always exists a basis. Okay, but just be careful. Of course, you will not be surprised to know that the basis is not unique, of course, highly non-unique. Okay, the basis is a special choice that we make. Okay, so this is a choice. The basis is not a property of the vector space. It's not like you have to go looking for the basis. That doesn't make any sense. You have to choose a basis among all possible bases. Okay, so yeah, okay, so here's the proof. Proof is very, very, very simple. Okay, so let's just, I'll take this opportunity to just mention something which is very confusing, but if you go through the definitions carefully, you'll understand why this is the case. But if V is the zero vector space, I'm just going to start with the very simplest possible case where the vector space is 0. Okay, so there should be a basis in this case. Then the empty list is considered a basis. Is a basis. Okay, so there's a couple of definitions that you need to check to make sure that this is consistent with everything that we've assumed so far, but the basic idea is that an empty list is considered to be linearly independent. Okay, and yeah, so anyway, I don't want to dwell on this particular thing, but yeah, you have a basis if the vector space is 0. So otherwise, we can express V as the span of a spanning list, where the VI's are non-zero. Okay, why is that the case? Well, first of all, the vector space we're assuming is finite dimensional, which means that it has it can be spanned by a finite list. So, and if 0 occurs on that list, then I'll just delete it from the list, and it won't change the span. So I don't want to have any I don't need to have any zero vectors on this list. So I might as well remove them if they happen to occur for some bizarre reason. Okay, and then for each v2, v3, and so on up to vn, what we could ask is whether it is in the span of the previous vectors. Of the previous vectors. Okay, if so, just remove it. And this doesn't change the span at all. This is part of the lemma that we proved last Tuesday, right? So if we find a vector which is in the span of the previous, we just remove it, and we just go successfully through the list this way. If not, keep it. Okay, and we just go through the list from left to right, checking this condition. So at the end, so after this, the span is unchanged. And no vector is in the span of the previous. Okay, so therefore by the lemma, the resulting list is linearly independent. Because in the lemma, we proved that if the list is linearly dependent, there must exist a vector which is in the span of the previous. And we know that's not true. So that means that it cannot be linearly dependent. It must be linearly independent. So therefore, we have a linearly independent list which spans V. So we have a basis. Okay, I just want it to be a little bit pedantic, going through every step here. Okay, so let me just okay, any questions about this? So we've proven that every finite dimensional vector space has a basis.
So Shreya has a question.
Okay, yeah, go ahead.
Hello, can you hear me?
Say again?
Hello?
Yeah, now I hear you.
I see. I had a question based on a comment you made.
Yeah.
So if we had a vector space that is not finite dimensional, would you be able to span it? Like, would you break it into parts or something?
Well, yeah, okay, so you're okay, so
Sorry if that's a little irrelevant.
it's a little bit out of the scope, but it's fine because it's a natural thing to wonder once we, but okay, so let me just explain a few things. So if the vector space is infinite dimensional, okay, this means that you cannot find a finite list whose span is that vector space, okay? Now, so you might ask, well, okay, what about if you could find an infinite list of vectors which span it? Well, okay, then you need to worry about what do you really mean by span of an infinite list, right? So if I gave you an infinite list of vectors, right, I could give you, does span mean that you're allowed to take only finite linear combinations of the elements of that list, right? So are you allowed to take infinitely many elements in the list and sum them all together? does that even make sense, right? How do we take an infinite number of sums, right? In analysis, you learn about limits. You learn about partial sums, because in analysis, you do this all the time, right? You take an infinite sequence and you try to sum it. And for that, you need to understand limits. And for that, you need to understand the notion of distance, right? So you say, I'm going to take partial sums. Each partial sum is well defined. I take a finite sum of elements, right? And I get a sequence of points, and then I need to show that that sequence of points has a limit. If it doesn't have a limit, then you might try to complete it. So you see that in order to do things with infinite lists, you need to invoke certain parts of structure which we don't have yet. We don't have the notion of distance. We don't have the notion of limits. None of that do we have. Okay, so there are ways of dealing with infinite dimensional vector spaces. The most famous of these are Hilbert spaces, infinite dimensional Hilbert spaces, or Banach spaces. But we're not going to talk about those in this class because there's somehow simpler stuff that is still unknown to you. So we need to get through that stuff before you move on to infinite dimensional vector spaces.
I see. Thank you.
Just in short, all of the definitions here that I'm using need to be modified slightly in the infinite dimensional setting, and it's not trivial. You need to add more structure. Okay, so just because I have some things that I need to get to today, let me just do one extra piece of theory, and this is another thing that we use a lot, and that is that so you see, how did we get this basis? This is the pessimistic approach. Okay, someone tells you that the vector space is finite dimensional, so you take a random spanning set of 1 billion vectors, okay, and then you start scanning through it and checking linear dependence. If there's a linear dependence, if there's a redundancy, you fire that person, and you just keep going and eliminate until you have a minimal set. So that's like, you start with more than what you need, and then you just discard. Okay. There's another way of doing it, which is, suppose that someone gives you, suppose you're trying to build a basis. Well, what you could try to do is start with one non-zero vector, at least just one non-zero vector, and that will span, a line inside the vector space. And then what you do is you take another vector which is not in the span of the first, and then you take another, you know what I mean? So you build it in this way, in an optimistic way. You build a basis. So this is the, maybe this is like the pessimistic approach. Okay, and this is the optimist approach of building the basis. Okay, but as you'll see, there's not really that much of a distinction between them. But anyway, let me give this anyway. So the theorem is that any linearly independent list in a finite dimensional vector space can be extended to a basis. So extending a list just means that you add more elements to the list without modifying the ones that you have already. Okay, so the point is that if you have a linearly independent set, a linearly independent list, you can grow it until it becomes a basis, and you never have to fire the people that you started with. Okay, so the proof of this is that, let's say that you start with a list. So if V1 up to Vm is linearly independent, okay, then we need to grow it. So where are we going to get our growing, where are we going to get these extra vectors? Well, we need to use somewhere the fact that the vector space is finite dimensional. So let's say W1 up to Wn be a spanning list. Okay, so I'm going to use a spanning list, and I'm going to go through that spanning list and try to look for candidates to add to my list so that it becomes a basis. Okay, so so you're basically interviewing some new workers, and you know that the workers together will span the whole space, but I just want to pick, you know, a few extra people because I already have some people that are spanning a nice subspace in a linearly independent way. Okay. Okay, so step one, okay, is that we're going to check if W1 is in the span of our linearly independent set, linearly independent list. If so, let me give this a name. Let me call this B. It's our candidate basis. Okay, leave B alone. Leave B unchanged. If not, just append W1 into the list. Okay, so now B, so the new B is now going to be V1 up to VM and W1. Okay, so I've lengthened the list by 1. And then step J, I'm just going to go through my spanning set, W1, W2. Okay, and at step J, we do the same, we basically do the same thing. If Wj is in the span of B, if Wj is in the span of the latest B, the one from step J minus 1, then we leave it alone. If not, you just add it as before. Okay, and so at the end, finally, after n steps, we have, by the lemma, a linearly independent set, linearly independent list. Okay, because remember the lemma tells you that in order for this thing to be linearly dependent, each vector, there must be a vector which is in the span of the previous, but we constructed this thing specifically so that that could never happen, right? It will never happen that that one vector in the list will be in the span of the previous just by construction. And so the lemma tells us there's no way there could be any redundancies here once we do this. But then we have that it's a linearly independent list, but the span is equal to the span of the W1s by constructions. And so this is a spanning list. So it's a linearly independent spanning list. So we've constructed a basis. This procedure is called basis extension. It's extending a linearly independent list longer and longer until it becomes a basis for the space. And this is it's an algorithm which terminates, you know, after this n number of steps. Okay, I'll take a couple of questions before moving on.
Okay, so Dixchant has a question.
Yeah, hi. So can you just briefly explain what is the main difference between a list of linearly independent vectors and then a basis?
So, okay, let's say that we're talking about R3. Okay. This is an empty list. Number 1. Okay, this is linearly independent. let's say I take a list which has this non-zero vector on it. This is a list of one vector. Here's 1, 0, 0. Okay. This is linearly independent. Okay, why is it linearly independent? It's because there are no redundancies here. Okay, if I take A times 1, 0, 0, and if I have a multiple of 1, 0, 0, which is 0, then A must be 0. So that means that there's no way of taking a non-trivial combination of the vectors which equals 0. Non-trivial here means that the coefficients are not necessarily all 0. The coefficients are not all 0. That's what I mean. Let's take the list 1, 0, 0 and 1, 1, 0. Okay, can I find a combination of these two vectors, which is 0, but where the combination is non-trivial? So in other words, if I take A plus B equals 0, right? Can I do this in a way? Can I do this in any way? Well, the answer is always yes. I can always take A and B to be 0, both of them, but that doesn't count. Okay, that's called a trivial linear combination. You're just taking 0 plus 0 plus 0. What's interesting is whether I can have a non-zero sum, a sum of non-zero elements, at least some of them being non-zero, which equals 0, right? That's a redundancy in the sense that, that I could solve, so in this particular case, what do I get? I get A plus B, B 0 equals 0, 0, 0. So can I find A and B which satisfies this equation? Well, the only way this is possible is if, first of all, B is 0, and number 2, if B is 0, that means B is not here, and then A would have to be 0. So that means that the only way for me to take a combination of V1 and V2 to be 0 is if I took 0 as the coefficients. And that's telling you that they're efficient, that there's no way for me to express V as a combination of the V1. Sorry, there's no way for me to express V1 as a multiple of V2 or V2 as a multiple of V1, that they're pointing in different directions. That's what linearly independent means. Okay, and then finally, if I take 1, 0, 0, 1, 1, 0, and 1, 1, 1, for example, okay, then you can see here that, well, I claim that this spans all of R3. Okay, maybe it's not completely obvious, but you could check that if I gave you a random vector A, B, C, right, you could write it as if this was V1, V2, and V3. Sorry, that one looks a bit weird. Right, then this would be C times V3, right, plus, what would it be? B, C times V3 times B minus C times V2 plus, well, what is it? A minus B minus C V1.
Wait, how did you get all these?
Well, I'm just guessing, and it's a good guess, hopefully.
Wouldn't B minus C be in brackets? Because you have to subtract them first.
Yeah, thank you. Okay, so I'm just saying that this has the span of R3, but they are also linearly independent, using the same argument as before. If I take a multiple of this plus a multiple of this plus a multiple of this is equal to 0, then all the multiples, all the coefficients must be 0. So that means that there is no non-trivial way of combining these vectors to get 0. So these vectors are efficient. They form a basis. Okay. So
shouldn't the coefficient of V1 be just B minus B?
You know what? It's not important. I'm just trying to give it's good that you're checking, but the point is that this is a linearly independent spanning set, so it is a basis. This is a linearly independent set. This is a linearly independent list, and this is a linearly independent list. But you only get a basis when the linearly independent list is big enough that it spans the whole space.
Yeah, okay.
Okay?
Yeah, I got it. Thank you.
Okay, so okay, right. So we now have the notion of a we now have the notion of a basis. We know what it means to be finite dimensional, that it has a spanning set, and we know that any spanning set can be whittled down to be a basis, and so we know that every finite dimensional vector space has a basis. Okay, and the dimension. So if V, so let me give the definition. Okay, and this is a little bit of a tricky definition for a reason that I'll get to in a second. So let V be a finite dimensional vector space. The dimension of V is the length of a basis for V. So it's the number of elements inside, it's the cardinality of a basis. Okay, but yeah, it's the length of the list. So for example, the zero vector space, it has an empty list as a spanning set, as a basis. So it would have length 0, and so it would have dimension 0. On the other hand, for f to the n, we see that we have constructed a basis, okay, and the length of the basis E1, E2 up to En is n. So we say that f to the n has dimension n. Okay, so the tricky part of this definition is that you need to explain why it is actually a sensible definition. Okay, because it could be, you could, if you didn't know any better, you might think that, okay, maybe you started with one spanning list, and you whittled it down to get a linearly independent spanning list, and so you got a basis. And maybe I started with a completely different spanning set, and I whittled that down, and I got a basis. So we know by the theorem that we can do this, that no matter what spanning set you initially chose, you can always reduce it until you get a linearly independent spanning list. The question is, well, okay, if you define the dimension to be the length of your basis, and if I define the dimension to be the length of my basis, how do we know that they are the same length? How do we know that there is a well-defined length, right? How do we know that every basis has the same length? So this definition depends, on the fact that that all bases have the same length. All bases of V have the same length. Otherwise, it makes no sense. It would be ill-defined. Okay, so in order for this definition to make any sense, for it to be a true definition, we need to check first that the length of any basis are all the same. Okay, and so this is, of course, in the textbook, but you should go through it, and I'll make some comments about it next week. But just before we stop for today, I just wanted to inject a tiny little bit of information which you should start thinking about. Let's just go back a little bit. I just want to make some comments about explicit subspaces. Okay, so let's suppose that you're dealing with a vector space f to the n. Okay, I'll just draw a kind of cartoon picture of f to the n, like this. Okay, so remember that we spoke about two ways of building subspaces. One of them was the optimistic way. So subspaces. In order to get a subspace, one way to do it would be to give a list of vectors. We could say that consider the list, the span of a list, vk, let's say, where v1 is a let me put it like this, a1 a n, where the AIs are in the field. So I've given you one vector, okay, and we're going to be taking all linear, multiples of that vector. I'm going to give you another vector, let's say b1 up to bn, where the bi's are in f, right? And I give you this data. You're going to see, and suppose I had stuff here which I'm not drawing, okay? So notice here that the information that I'm providing to you is a bunch of vectors, something like this. Okay, let's say v1 all the way up to vk. I give you this list and I say, take the span. That will give you a subspace. That will define a subspace. Okay, so that's the optimistic approach. And notice the data. What is the data that you need to specify to me? You need to specify n numbers in the field for each vector in your list. Okay, so that's an n by k array of numbers, like a1 up to an, b1 up to bn, all the way down to c1 up to cn. So this is a k by n grid array of numbers in the field, and you have to give me that information. If I have that information, then you can take the span of those vectors, and you will get a subspace, a linear subspace. Okay, so you can see how the data determines that. So just a k by n grid of numbers. So this whole here is a k by n grid or matrix of numbers. We're going to get to this in great detail later. Okay, but there is another pessimistic way of doing it, which is to say, alternatively, okay, what I can do is I can give a1 up to an, where ai is an f, okay, b1, same information. And instead, what I could do is look at the set of x of points inside the vector space, the set of vectors, such that a1 x1 plus an xn is equal to 0, and b1 x1 bn xn is equal to 0, and so on. Okay, this is saying that I'm going to look at only the vectors which satisfy this constraint, and the constraint is cutting down, right? It's imposing a constraint. It's saying, no, I'm eliminating all vectors that don't satisfy this constraint. I want everyone to satisfy this constraint, and you just keep constraining the thing, cutting down the size of your subspace, getting smaller and smaller. So you see here, the more of these data that I provide, the bigger the subspace gets. And here, the more of these data that I provide, the smaller the subspace gets, because it gets more and more constrained. Okay, so we need to start talking about these two methods, because these are the two main methods of determining subspaces. So we need to be able to operate with this, and we need to understand how this works. So this is called a linear system of equations, and this is just giving a spanning set. So we need to be able to do both. Okay, I'll leave it there. And we have office hours, so let's we'll have an hour of questions. But just for those people who can't stay, if you cannot stay for the office hours, try to ask your question right now so that I get to it. And if you're going to stay, then just wait a few minutes before asking your question.
Okay, so Angela has a question.
Yeah, hello.
Hi.
I'm just wondering, when we were talking about the proof of the theorem that every finite dimensional vector space has a basis.
Yeah.
At the very last step, you said that after n steps, we get like the linearly independent list, which spans V, which is like W1 to Wn. I'm not quite sure. Like, I didn't really follow that part. Why is it W instead of the original B that we had plus all of the W's we added?
Okay, sorry, you're talking about the second theorem. You're talking about the fact that any linearly independent list can be extended to a basis. Okay.
Oh,
so,
yeah.
So the idea, I'm not saying that the W's are the list. I'm saying that I'm trying to, let me just put, there's two things to remark. So after n steps, what do I have? I have the V's, which I started with. Those were the linearly independent vectors. And then I added, I was careful to add a sequence of vectors to it, which didn't ruin the linear independence. So I just kept adding vector W's, some of them, a selection of them. I added ones that would maintain the property of being linearly independent. And at the end, I'm going to have V1 up to Vm and then a few of the W's. Okay, so I'm going to have, as you said, that's what I'm going to have. Now, at the end, what do you need to know about that resulting list? So at the end, after n steps, the list looks like this. It looks like V1 up to Vm. And then you have some of the W's, Wi1, Wi2. We don't know exactly which ones we're going to keep, but some of them will be on the list, right? So at the end, this is what I'm going to have, something that looks like this. Are you okay with that so far?
Yeah.
Okay, then what do I need to do? I need to check that this is a basis. So number one, I need to check that this is still linearly independent. And I use the lemma for that, because lemma says, well, okay, what are you afraid of? I'm afraid that they're linearly dependent. But in order to be linearly dependent, there's got to be a vector which is in the span of the previous. But I constructed this so that that does not happen. So therefore, it is linearly independent by the lemma. Okay, the second thing I need to check is that it still that it spans V, that the span of this list is V. Notice that the span of the first part is not V necessarily. I mean, it's not necessarily spanning V, this part. This part could have been empty as far as we know. This initial list could have been empty. Okay, what I want to check is that this whole thing spans V. And the reason that that's true is because of the fact that we assume that the W's span V, right? And so what I'm doing is I'm adding all of these vectors to my list. Well, I'm not adding all of them. I'm only adding the ones that I need to add in order to span V, right? So every one of these vectors is in the span of this. So let me put it that way. The span of W1 up to Wn is inside the span of V1 up to Vm, Wi1, Wik. Okay, and this is equal to V. So there's no question that, since each one of these vectors is in this span, okay, that means that V is contained in the span, and therefore that list is a spanning list.
Oh, okay, that makes more sense. Thank you.
Yeah. I was just commenting on the fact that the reason that we know it spans is because the W's span. Okay, next.
Okay, so Lauren has a question.
Yeah, hi, Professor.
Hi.
Could you scroll down to the bottom? I want to take a screenshot.
A screenshot? Why?
Yeah.
I'm providing these notes, no?
Because I'm taking my own notes. So,
Okay.
yeah, I'm done. Thank you.
Okay. All right.
Okay, so Howard has a question.
Hi, Professor. So
Hi.
I'm still kind of confused about the very end, like when you say like this kind of constraint is being put into the list. Like, why is this specific constraint that we are like putting? Like
Okay,
A1,
so
X1,
what I'm talking about here, I wanted to, I just wanted to introduce an idea for you to think about, okay? Because we're going to talk about a lot more about this, okay? And it has to do with the fact that if you're trying to describe a subspace, right? If you're trying to describe a subspace, like for example, suppose that I wanted to describe this subspace. This is, let's say X, Y, Z. Okay, in red, I've colored the XY plane. Okay, now first of all, XY plane, is it a linear subspace of R3? So the XY plane inside R3. I claim that this is a linear subspace. Do you agree?
Yes.
Okay, so so the question is, how do I mathematically, how do I indicate, or how do I write down this subspace? How do I build or construct this subspace? Okay, so there's two options, fundamentally different options. Okay, to describe this subspace, number one is as a span. Okay, and how would we do that? Well, you need to make some choice of spanning list. So I have to take, two, oops, great. I have to take two vectors in here. I have to take, let's say, this one and this one. So I could say that it's the span of, let's say, 1, 1, 0, and let's say 1, 2, 0. You may think that my choice of spanning list is a bit weird. You might prefer, for example, 1, 0, 0 and 0, 1, 0. Maybe you prefer that spanning list, but there's no reason why we should prefer one over the other. Okay, so in order to give this data, what did I need to give? I needed to give the following numerical data. This has to be input into the computer somehow.
Yeah.
Okay, and you could say, well, okay, you made a kind of boneheaded choice. You should have entered into the computer instead this, because the span is the same.
Mm-hmm.
Okay, so this means that we need to understand that when we specify a subspace by giving this data, okay, that we need to understand when are the results the same, right? How do we know that this data and this data give the same subspace, right? We need to have some kind of understanding, theoretical, of why this data and this data specify the same subspace. Okay, but anyway, I'm just pointing out that this is one way to do it.
Mm-hmm.
Okay, now there's a second way, as a constraint. Okay, you could look at the set of points such that they satisfy a constraint. So what is the constraint that all of the red points satisfy?
Z equals to 0.
Yeah, so I take 0 times x plus 0 times y plus 1 times z is equal to 0. So from this point of view, the data that I gave was this data.
Yeah.
Okay, but it's a different It's a different point of view. It's a different way of constructing the space, right? So you need to know which algorithm you're using. You're using the optimistic algorithm, which is looking at the span of the stuff that you give me, or you think of it as a constraint and you cut down, right? So you know, there's advantages and disadvantages to both ways. So let me just give you another example. Suppose that I give you the constraint, the set of x, y, z, such that x plus y plus z is equal to 0. Okay, this constraint, well, okay, I mean, let me give you another example. Let's look at the xy plane and look at the set of xy such that x squared plus y squared is equal to 1. Okay, the points which satisfy this constraint is a circle. Okay, so the problem, you know, the thing you need to be worried about with constraints is that if you just write down a general constraint, that constraint will not give you a linear subspace. It could give you anything. I mean, it could give you all kinds of crazy stuff, like a circle, which is not a linear subspace of R2, right? So this type of constraint is not one that we are going to consider. We need constraints that look like this, okay? And these are what are known as linear constraints or linear equations. Okay, so what does it mean to be a linear equation? It means that if you find a solution, then you can multiply that solution by a number and you get another solution. Or if you have two solutions, you can add the solutions together and then the sum will be a solution, right? So in other words, the solution space is a linear subspace. That's what it means. Okay, the solution space to this is equal to a linear subspace. And what does that linear subspace look like? It looks like, well, it looks like a plane, okay, which intersects the origin and which is not lying in any of the coordinate planes. Okay, so there's a slight disadvantage to writing it in this way, because if you write it in this way, you will not have at your disposal, at your fingertips, you will not have a list of vectors that is in that subspace. You will not have a spanning set. You will not have a basis, right? So, you know, if you want, you could think of it this way, that when I write down a constraint like this, what I get is a subspace of R3, but this subspace is you know, it's very different from R3 in the sense that R3 had a canonical basis. It had a natural basis where you just took, you know, the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. You had special quote unquote unit vectors that span the space. But this one does not have any special basis vectors. Okay. So that's what happens when you find new vector spaces by imposing constraints, is that they become a little bit more abstract in the sense that they don't have a preferred basis that you can rely on. And so I could ask you a question right away. I could say, find a basis, you know, find a basis for U. That would be a good question to ask. In other words, can you now take this subspace U and write it in terms of a span, right? That requires some kind of computation. It's not like you can just stare at this and give me the answer, right? You need to do some kind of algorithm, or you need to understand some piece of theory in order to go between these two methods. And that's one of the tools that we'll have.
All right, thank you.
Okay, so Omar has a question.
Professor, it's not really a question. Does the linear equation, the x plus y plus z equals 0, like this whole concept, will it end up eventually leading to a linear system of equations when it comes to solving in matrices and all that?
Yeah, that's what we're doing. So when you put a linear system, just means that you have more than one of these constraints. So if I put another constraint, let's say, let's put both of the ones that I looked at. So let's look at W, which is the set of, so what did I have here? Let me call this one, let me call this one W, the span there, and let me call this one U, and let me call this one X. So X will consist of the set of X, Y, Z such that Z, 0 times X plus 0 times Y plus 1 times Z is equal to 0. And also X plus Y plus Z is equal to 0. So I'll just put the coefficients here so that no one is confused. The coefficients are all 1. So now I have two constraints, okay? Now, so if you have a point which satisfies this constraint and this constraint, and you find another point which satisfies these two constraints, well, what about the sum? The sum, we already understood that this is a linear constraint. So if you have 2 points satisfying it, then their sum will automatically satisfy this constraint. And the same is true here. So when you place several of these linear constraints, what you're really doing is you're just defining a linear subspace. This defines a linear subspace of R3. Okay, and what is that linear subspace? Well, it consists of the points which satisfy this and this. Okay, well, if it satisfies this, that means that it is in this space. It is in W. So this is the same thing as saying this constraint here is saying that this is equivalent to X, Y, Z in W. And this one here is the same as X, Y, Z is in U, this U here. Okay, so that means that this space is nothing but, the set of X, Y, Z such that it's in W and in U. So in other words, we have X is U intersect W. Okay, it's the combination or the imposition of two constraints. This is the first constraint, and this is the second constraint. And when you have a system of linear equations, you're simply intersecting a bunch of subspaces, one corresponding to every constraint. Okay, so what will that look like? Inside R3, you will have, first of all, you'll have this U space, U, and then you will have W. That's U and W. And then the way that they intersect, well, how do they intersect? Well, it's going to be all the points where Z is equal to 0. Okay, but Z is equal to 0, and then X plus Y is equal to 0. So that means that X is going to be equal to minus Y, right? And so the way it will look is exactly like this. Inside here, you'll have a subspace, which is a line. And this here is X. Okay, so we have two planes which are intersecting in a line. So you should think that this linear equation is defining a plane. This linear equation is defining a plane. And to impose both constraints means that you're intersecting the two planes, And in this case, the intersection of the two planes is a line. That's what solving linear systems is all about. It's about taking a bunch of planes and intersecting them and seeing what you get.
But the constrictions, the constraints have, how do they affect the span, or they don't?
Well, this is what I was talking about here, right? That
Yeah.
that you have two choices in how you describe your subspace. You could either describe it as a span of a list of vectors, or you could describe it as a sequence of constraints. And those two ways are, you can go between them, right? But you need to know how. It's not obvious how to go between them. So for example, here I could ask you the question, I gave you the two constraints. Okay, you take the intersection of them, you get a subspace, the green subspace. Now I ask you, find me a vector that spans this subspace. What I'm asking you is to find a solution to both of these, right? And that's not obvious. You can't just stare at this and immediately know the answer, especially if this was, 50 equations in 100,000 unknowns, right? You need to have some method for figuring out a vector, for finding a vector in here, right? Some vector which spans that one-dimensional subspace. So, to be continued.
Thank you.
You're welcome.
Okay, so Bin has a question.
Yeah, Professor, hi, Professor, can you
Hi.
go a little bit? Just go up. Yeah, and keep going, and keep going, keep going. Yes, right here. Like I am little bit confused about, yeah, how can you just compute the coefficient like a plus b? So how can you compute it? I'm a little bit confused about it. Like a plus b and then b and
Okay,
0.
just one second.
Yeah, how can you get this computed?
So, okay. So here we need to decide which vector space we're working in. We're working in R3, okay? R3,
Yeah.
an element of R3, what does it look like? X, Y, Z, where X,
Yeah.
Y, and Z are in R, okay? And this has vector space structure. So in other words, we know how to add them. We know how to do a scalar multiplication.
Yeah.
So if I take a scalar, A, and if I multiply it on this vector, what do I get? What is the definition of the scalar multiplication on R3?
A00. Yeah.
A00 plus B0. Okay.
Yeah,
And then what is the definition of sum? I'm supposed to get a single vector as the sum of these. So
I got it.
you have to add them component wise.
Oh, okay, I got it.
Okay.
Okay. Still, yes, a stupid question.
It's okay.
Okay, so Shreya has a question.
Hello. Sorry
Hi.
if this is slightly stupid, but
All right. All questions are stupid from the point of view of general artificial intelligence, which we will one day have. Don't worry about it.
So in Axler, he talks about how the P sub MF, like the polynomials, are
Yes.
like a finite dimensional vector space. And in our assignment, we saw two of those things. But I was wondering if you wanted to prove, like in general, that polynomials there exists a multiplicative inverse. How would you do that for them?
Wait. Sorry, slow down for a second.
Okay, sorry.
What is your question? So you want to prove what?
That they have like every vector there has a multiplicative. Oh, never mind. My question was stupid. I think I realized.
No, what was the question? The question was about whether polynomials of a fixed degree or polynomials of degree less than or equal to k, whether they have multiplicative inverses.
Yeah, it was in relation to assignment too, but then I realized vector spaces aren't fields. So yeah.
Right. So the polynomials will not have inverses like that.
Yeah.
But I guess the one thing that you could try to show is what the dimension is. Like, for example, if you had P, I forget what the notation that he uses. Maybe it's like this. So these are polynomials of maximum degree K with coefficients in F, right? You could ask, what is the dimension of this? Okay, so technically speaking, we have not defined fully the notion of dimension because we haven't proven a relatively easy fact, which is that once you find a basis, then the length of that basis is, it doesn't depend on which basis you picked. That if you give me two different bases, they will always have the same length inside the same, when they're in the same vector space. And so if you wanted, what is the dimension of this space, by the way?
K.
What is a basis for it? Give me a basis. A basis should be a list of vectors which span the space and which are linearly independent. So give me a list of polynomials which span the polynomials of degree less than or equal to K.
So 1, I guess, x.
That's another
and,
one, yeah.
And then x to the power of 2. And then you keep going till you reach x to the power of k.
Okay, and so what will be the length of this list of vectors?
It has k plus 1 elements.
Thank you. So the dimension should be the dimension of p less than or equal to k should be what?
K plus 1.
K plus 1, yeah. Correct. Okay, but this is only one possible basis, right? I mean, I could take something like this. I could take 1, x plus 1, x squared plus x plus 1, x cubed plus x squared plus x plus 1, right? All the way to x to the k plus x to the k minus 1 plus x plus 1. This would also be a basis. It would be a different basis. Okay?
I see. Thank you.
Okay, you're welcome.
Okay, so Leo has a question.
Hello.
Hi.
I had a question regarding like when we take a vector space of polynomials, why we consider that as infinite, but when we take a list of vectors from V1 to Vn, why we consider that as finite?
Okay, so if we're dealing with polynomials with coefficients over a field, this is a vector space over F. It's a vector space, and so when you ask the question, is this vector space finite dimensional or infinite dimensional? Okay, what does that question mean? The question, what it means is whether you can find a finite list of elements, right? I need to find V1 up to Vm, where the Vi's are polynomials. So I need to find a finite set of polynomials such that any polynomial can be written as a linear combination of those. Okay, such that P of F is the span of V1 up to Vm. Okay, so that means that any polynomial at all, no matter how high the degree, has got to be a linear combination A1 V1 plus AM Vm, where the Vm are fixed. They have to be completely fixed, and they need to be able to generate every polynomial. Okay, so this is a losing battle because suppose that V1 was a polynomial, right? It has to be, what is V1? V1 looks like, it looks like, let's say A1 X, let's say A0 plus A1X plus A2X squared plus AD X to the D. That's what V1 has to look like. Okay, and so that means that there will be a maximum degree for V1. V1 has a maximum degree D1. Let me call it D1. Okay. So each one of these will have a maximum degree. This will have maximum, VI has maximum degree DI for some DI. Okay. So now when I take a combination like this, let's say, sorry, this is not very visible. When I take, let's say, lambda 1 times V1, right? This lambda 1 is just in the field. So this is like lambda 1 A0 plus lambda 1 A1 X plus lambda 1 A D1 X to the D1. I'm just multiplying all the coefficients by lambda 1. Okay, so when I take a linear combination, lambda 1 V1 plus lambda n Vn, okay, this term has maximum degree D1. This one has maximum degree Dn. So the whole thing has maximum degree, whatever the maximum of D1 up to Dn is. There's no way to get a polynomial of degree, bigger than all the Dn's. Right? So there's going to be plenty of polynomials of very high degree, which are not in the span of this finite list. So you're going to fail to capture all polynomials with a finite list. Does that make sense?
Yeah, that makes more sense. Thank you.
So that's why it fails. That's why it has to be considered infinite dimensional, because you can never capture all polynomials with a finite set. That's why, you would need to have an infinite list. And so you would need to have an infinite basis if you wish, although we haven't defined what that means. But anyway, it's clear that here you will not be able to succeed with only finitely many polynomials.
Thank you.
You're welcome.
All right, so Omar has a question.
Yeah, I feel like I'm raiding this office hour. I feel bad.
It's okay. There's only one other question. Yeah, people should don't worry about. Oh, should I stop the? 1 second. I should stop the
recording.
The live stream. Yeah.